All right, and so doing this problem, the first thing we want to do is we want to go back to our general equation for compounding interest. And so hopefully as you take a look at this, your brain is brought back to those notes that we have from earlier, where we have that a of t equation. Remember that p times 1 plus r to the t? We're going to be using that here. In this case, what's p? 150, yeah, because p is always our starting amount. What is r? Potentially slightly trickier because, yeah, it's 4%, but I'm not going to put 4% in for r. I'm going to turn it into a decimal. So take your 4 divided by 100, and that gives you 0.04. That's 4% as a decimal. And then t is what we don't know. So then where do we put our 350? So I take my equation, I went ahead and I did the 1 plus the 0.04 just because it's going to make later calculations easier. And we can take that 350, that's the final amount that we're looking for, and I can plug that in for the a of t. So now this is our equation that we start with, and then now the one that you are solving. So from here, we actually need to go through the whole process of just solving the equation. Remember when solving one of these that has the unknown and the exponent like that? I want to get that exponential part by itself first. That means getting rid of the 150. I divide both sides by 150, which gives me 2.3 repeating equals 1.04 to the t. You want to keep that 2.3 repeating up on your calculator. Even if you just write down 2.3, make sure that in the calculations to come, that you keep that decimal actually in there. Otherwise, you might end up with some rounding error. All right, so from here, I now have the exponential part by itself over here, which means now I take the new step for this year, which is that in order to solve for an exponent, I turn it into a logarithm. So I write as a logarithm there. T equals log base 1.04 of 2.3 repeating. In order to do that calculation, you should be using that change of base formula, where we do log divided by log. And if all goes well with that calculation, you should be getting an answer of about 21.60. If you did this calculation without using the whole decimal, the 2.3 repeating that your calculator left in there for you, if you just called it 2.3 instead, you get rounding error in this problem. Specifically, instead of getting 21.60, you get 21.24. It's a decent sized difference in terms of the actual answer here. And so, again, make sure you use the exact number. If you're using a TI-84 or TI-83, that means that you really need to make sure you know how to use the answer key. It's second negative. Remember, that key will put in whatever the last answer was, and it puts in the whole decimal for you, so you're not like having to type in the whole thing around it or anything like that. It gives you much more precise answers as you're doing some of these. All right, so the work that we're going to be heading into today is actually going to be some logarithm rules. And you're going to find that the logarithm rules are closely related to the exponent rules. So I'm going to start by going back to these. And just remembering, how do the exponent rules work? So for instance, in this first one, if I have x to the a times x to the b, in other words, if I'm multiplying, what do I do with the exponents? What would I do with the a and the b here? We'd add them, exactly. And so if I were writing this as a general rule, then it would be x to the a plus b. All right, what about division? If I divide, what do I do with the a and the b? We subtract, absolutely. And then what if I have a power to a power? Yep, it's multiplication. Very good. You'll notice that with each of these, multiplication goes to addition. Division between the x's becomes subtraction in the exponents. Exponents become multiplication. One way that I will sometimes think about this as a side note is if you think of the normal order of operations, PEMDAS, you'll notice it's like we're stepping one step down for each of these. So like exponent becomes multiplication. Multiplication goes down to addition, that sort of thing. It's just stepping one step down in the order of operations as a way to remember it. Now those same ideas come into our logarithm rules, which we're just going to start as just writing down the rules. But you'll notice multiplication goes with addition, division goes with subtraction, and an exponent goes to multiplication. All right, so we're going to take a look now at doing each of these using our rules. So the first thing we have to do is taking a look at this first problem, log base 5 of 25x, is I have to decide which rule I'm going to use. Now notice the log base 5 part, that's all normal. What's different from it just being a very basic problem is the fact that it's actually 25x inside instead of just a 25 or just an x. Well, this means multiplication. It's 25 times x. So that tells me to go to this rule, where if I multiply two things inside of the logarithm, I can turn it into two separate logarithms that are added. Notice that in each of those logarithms, they both have the same base b. That's the same as what the original was. So I know that when I write this, I'm going to have to end up writing log base 5 of something plus log base 5 of something else. Well, those two somethings are the two things that were multiplied inside of the parentheses. So it's got to be the 25 and the x. And so then this is what we get when we just break it up according to that rule, is log base 5 of 25 plus log base 5 of x. Now one of the advantages of doing this is that oftentimes as a result of that we can actually simplify something. And do you see in that line that we just wrote that there's something we can simplify? Log base 5 of 25. We can know what that equals. Because remember, log base 5 of 25 just means 5 to the power of what equals 25?
2.
So it's 2. Yeah. So really that whole thing just simplifies down to be 2 plus log base 5 of x. And so now we go on to the second problem, log base 3 of 9 over x. And again, I need to decide which rule am I going to use. The log base 3, that's all the same as it always is. The only thing that's kind of different or slightly more complicated than it has to be is this fraction inside of the parentheses. Remember that a fraction just means division. That's why this is our rule, because our fraction, our division, is going to become subtraction. So let's follow this rule to write our new rule. All right, so you notice that again they're both log base b. So when I write this, it's going to be log base 3 for both of them. Since it's division inside of the logarithm, I know that's going to become subtraction outside of the logarithms. And then what goes inside of my logarithms? Well, that's just the two things that were divided. Now, order does matter here. It didn't actually matter with the first one we did because it was multiplication and addition. But here it does matter. The 9 has to go first, and then the x. So we have log base 3 of 9 minus log base 3 of x here. And again, I want to look and see, can I simplify that at all? Is there anything here we can simplify easily? Yes. That log base 3 of 9. Because, of course, when I see log base 3 of 9, I know that means 3 to the power of what equals 9? And that's 2, yes, because 3 squared equals 9. So there's our answer. Nice and simplified. All right, now we go to the last one. And in this case, as I look inside of my logarithm, I'm looking to see what is beyond just there being just a number or just an x or whatever. And I see that this one is 64 to the power of x. So that means I have an exponent inside of my logarithm. Do you see which rule that tells you to use? Hopefully you're saying it's the one that we haven't used yet. Go figure, right? We got to use this rule. Log base b of m to the n equals n times log base b of n. In other words, it all is going to be exactly the same except that whatever the exponent is gets pulled out and multiplied by the logarithm. So you notice in this case, my exponent is the x. So the x is going to get pulled out and multiplied by the logarithm. So I have x times log base 4 of 64. Having gotten that now, again, I look and see, can I simplify anything there? Well, can we actually know what log base 4 of 64 is? It seems likely, right? Because that actually is it's just a number and a number. Well, 4 to the power of what would equal 64? 3, yes. 4 cubed is 64. So we get x times 3. Well, and of course that simplifies, that's just 3x. So that's what I'd love to see as a final answer there is 3x. And that one, of all of them, definitely shows how knowing these rules can make some of these that look complicated at first actually turn out to be very simple. So now we go on to these two problems. This first one here, notice we have log base 3 of x plus log base 3 of y. It's already adding. Well, that's because notice we're writing each expression as a single logarithm here. So basically, these two problems we're doing exactly what we did before in the last set, except backwards. We're trying to combine them into a single logarithm and see what that would give us. Okay, so if we do that then, first of all, I think about which rule am I going to need to use. Well, which one results in addition? It's that rule. And so, again, remember that the addition gets associated with multiplication. So I'm going to end up doing log base 3 of x times y, which is just xy. One little side note here. Both of these were log base 3. If they had different bases, we could not have done that. They have to have the same base here for us to be able to use this rule. All right, now on to the second one. As you take a look at the second problem, you'll notice we actually are going to end up having to use two different rules. Because we have both multiplication happening in front of the logarithms, and we have the addition happening between the logarithms. And so we actually are going to end up having to use both of those rules down there. The question often comes down to, well, which one do we use first? Well, if you're not sure, think about trying one. Because you'll find that if you try putting these together the wrong way, you're just going to be looking at it like, this just does not work. It actually does basically follow the order of operations going this way, where we're going to deal with the exponent / multiplication part first. And so the first thing I want to do is use this rule. Notice what that means I do. This 3, it's going to become an exponent. This 3 here, it's going to become an exponent. And so this is how I would write it out first. Now, having done that, I could go ahead and just jump into the next step of dealing with the addition, but I don't really want to, because I can clean this up a little bit right now. So let's do that cleanup. 2 cubed, I know is 8. 5 cubed, that's 125, so I can just turn this into log 8 plus log 125. It's already simpler, but I still do need to combine them and get rid of that addition. Notice I can do that because they have the same base. By the way, what is that base? 10, yes. If I don't write it in, it's assumed to be 10. That's why it definitely is the same for both. All right, and so the addition then, notice the addition becomes multiplication again. And so that ends up being 8 times 125, which is 1,000. So it's log of 1,000. Okay, can I simplify that? Well, remembering that this is log base 10, right? So that's kind of like saying 10 to the power of what would equal 1,000. Is that a nice, pretty number? And if you're not sure, you actually could type just log 1,000 in your calculator, as I know a couple of you have done, to just see, hey, that gives us a number. But yes, it actually is a nice, pretty number, because remember, anytime you multiply something by 10, you add a 0 to it. So like if I take 1 times 10, that gives me 10, because I just add a 0. Times another 10. 10 times 10 will give me 100. I just have to add a 0 on. 100 times 10 will give me 1,000, because I just add a 0 onto the end, which notice is what we're looking for up here. The cool thing about logarithms that are base 10 is however many zeros there are, that's how many 10s you had to multiply. That's why the whole answer here just ends up equaling 3. All right, so 2 more practice problems. Again, we're going to try to write each expression as a single logarithm, so I'm condensing in this case. Subtraction. Am I allowed to combine these 2 logarithms into a single logarithm here? Well, do they have the same base? Yes, they do. That means yes, we are allowed to do so. So it's going to be log base 4, but what do I do? What's subtraction become?
16.
The subtraction becomes division inside. And so it is 32 divided by 2, which, yes, many of you have already calculated straight down to 16. So it's log base 4 of 16. Okay, once again, can we simplify that? Can we actually figure out what log base 4 of 16 is?
Yes.
Is it a pretty number? Well, 4 to the power of what is 16?
2.
Yeah, I do know that one. 4 squared is 16. So it's got to be 2. All right, then on to the second problem here. Log 32 divided by log 2. We see division. And when we see division, our mind automatically goes to this, but this is a problem. Because this isn't actually going to work for us. Notice the difference. This one is a log divided by a log. This is a log with division happening inside of it. It's just a single logarithm, not 2. And so we actually cannot use this rule. And yet we do have a rule for that. In fact, you've used it today, where you did a log divided by log. Just you did it on your calculator. That's just change of base formula. So remember this formula from before. Just we haven't ever looked at it in terms of, hey, take it from this form and put it into this. But of course, it can work that direction. We can do that. And so we're going to take it from the division of logs into writing it as a single logarithm. Remember that the base always is the number that's on the bottom. And so you should be getting log base 2 of 32 here. Now we wrote it as a single logarithm. Can we simplify that? Do we know what log base 2 of 32 is? Yes, we do. It is 5, because 2 to the power of 5 equals 32. And yes, that is one of those values that comes up often enough. You should know it off the top of your head if you don't yet.